Imagine a light planet revolving around a massive star in a circular orbit of radius r with a period of revolution t. If the gravitational force of attraction between the planet and the star is inversely proportional to r to the power 5 by 2, then the square of the time period will be proportional to. And the options are r cube, r square, r to the power 2.5 and r to the power 3.5. Yes, in reality, the gravitational force is inversely proportional to square of the distance between the two objects. But here they have given an imaginary situation that if the gravitational force was inversely proportional to r to the power 5 by 2 rather than r to the power 2, then the square of the time period of revolution would be proportional to what power of r? That is the question asked, and let us answer. So here is a beautiful animation of a planet moving around a massive star, right? So it's going in a circular orbit of radius r. And now, if the gravitational force between these two is proportional to 1 by r to the power 5 by 2, then square of the time period of revolution is proportional to what? That is the asked question. So let us answer. Well, the gravitational force here must provide the necessary centripetal force, which is mv squared by r. Agreed? Now the gravitational force is some constant divided by r to the power 5 by 2 according to the problem itself, and that is equal to mv squared by r. So upon rearranging, I get v squared is equal to k by m into r to the power 1 minus 5 by 2, correct? R divided by r to the power 5 by 2 will become r to the power 1 minus 5 by 2, which is r to the power minus 3 by 2. Agreed? So what will happen to v? V will be square root of k by m, which is some other constant k prime, let us say. And square root of r to the power minus 3 by 2 will become r to the power minus 3 by 4. Square root means you're just taking the power of half, right? So it will become 3 by 2 into half, which is 3 by 4, of course, with a negative sign. So we have got the radial dependence of the velocity, the orbital velocity of the planet. Now we need to go for the time period. Well, the time period of revolution is time taken to complete one full revolution. So the distance traveled in one revolution is 2 pi r divided by the speed with which it revolves, which is the orbital velocity v here. Agreed? So we have 2 pi r divided by v. For v, we just got the result that it is some k prime into r to the power minus 3 by 4. So it is 2 pi by k prime into r to the power 3 by 4. That minus 3 by 4, when it goes to the numerator, becomes plus 3 by 4. So we'll have r into 1 plus 3 by 4, which is r to the power 7 by 4. That is t. So it is pretty clear that t is proportional to r to the power 7 by 4. But the problem doesn't ask for t, it asks for square of the time period. So if I square both sides, t square will be proportional to r to the power 7 by 4 into 2, which becomes 7 by 2, or r to the power 3.5, which is one of the options, isn't it? This is the required answer. If the gravitational force is inversely proportional to r to the power 5 by 2 in a circular orbit, the time period of revolution will be, or the square of the time period of revolution will be proportional to r to the power 3.5. That is the required answer for this particular question. T squared is proportional to r to the power 3.5. And which is the option that agrees with our result? Yes, it is option D. Force of gravitation between two masses is found to be F in vacuum. if both the masses are dipped in water at the same distance, then the new force will be, right? So here we have two masses separated in vacuum initially, and then both of them are dipped in a liquid, right? So water, and the distance between them is maintained the same. Then what happens to the new gravitational force? And the options are greater than F, less than F, equal to F, cannot say. Well, let us see that. Now we know that F is equal to G m1 m2 by r square. Agreed? Now in both these cases, m1 and m2 are the same. R square is also the same because the distance is maintained the same. So if at all the force changes, it has to change because of the constant of proportionality. But repeat along with me, what is G called as? It is called as universal gravitational constant. Repeat once again, universal gravitational constant, which means the value of G is universal. I believe, all of us must believe, that there are parts of universe which we haven't even seen through the light that comes through that. It's millions and millions of light years away. But still we believe, our belief in Newton is so strong that we call G as universal law of gravitation. Not Indian law of gravitation, not Asian law of gravitation, not the world law of gravitation, not the solar system law of gravitation, not the Milky Way law of gravitation, but universal law of gravitation. So in any corner of the universe you attempt this experiment, G's value will be the same. That's how confident we are about what Newton gave us, right? And that's the respect we pay to the great Newton. Agreed? So G is universal, unlike in electrostatics, wherein we get a similar type of force, which is the electrostatic force of attraction or repulsion. There, the constant of proportionality is medium dependent. But in gravitation, it is not the case. So since G does not change with the medium, masses are the same, the distance between the masses remain the same, the force does not change, it remains to be the same. And the reason being, the force of gravitation is independent of the medium. And which is the option that supports this idea? Yes, it is option C. 2 point masses m and 4m are separated by a distance d on a straight line as shown in the figure. A third point mass m, m0, is to be placed at a point on the line such that the net gravitational force on it is 0. Find r, where r is the distance from the third mass that you keep along the line joining the first two, and a distance r is from m and not 4m according to the diagram. And the problem asks us to find the value of r. And the options are d by 2, d by 4, d by 3 and d by 5. These are the 4 options. Let's see which one of them turns out to be the correct one. Well, we have placed m0 in between m and 4m. So obviously what happens is that 4m attracts m0 with a particular force, and m also attracts m0 with a force. Let's say this is F1 and this is F2. So the net force on m0 due to these two masses will be F1 minus F2 or F2 minus F1, whichever sign convention you consider, right as positive, left as negative, or the vice versa. But in this problem, we want that net force, which is F1 minus F2 or F2 minus F1, to be equal to what? 0. So if F1 minus F2 is 0, then F1 is equal to F2, right? That means the magnitude of the gravitational force of attraction between m and m0 and between 4m and m0 must be the same, right? Now, if this distance is r as mentioned in the problem, this distance will be d minus r. Now we know the masses, we know the distance. All we have to do is substitute for the force and solve for the value of r. And according to the options, we are clear that we should get R in terms of D, the distance of separation between M and 4M. So what are we waiting for? Let us start. So this is everything that we have discussed up until now. And for the net gravitational force on M0 to be 0, the magnitude of F1 must be equal to the magnitude of F2. So F1 must be equal to F2 in magnitude. F1 is the gravitational force of attraction between M and M0. So it is G M M0 by distance between them squared, which is R square, equal to F2 is the force between G 4M and M0. So it will be G 4M M0 divided by D minus R whole square. So G cancels out, M cancels out, M0 cancels out. So I will have 1 by R square is equal to 4 by D minus R whole squared. Solve for the answer. You will have 1 by R is equal to 2 by D minus R if I take the square root, but there will be a plus or minus. So I will have D minus R is equal to 2R, or D minus R is equal to minus 2R. So I'll get D is equal to 3R, or in other words, R is equal to D by 3, or from this, I'll have minus R is equal to D, or R is equal to minus D. But R is a distance that we have defined between two objects, and distance cannot be negative. Distance cannot be negative. So we do not consider this result, and the only result remaining is R is equal to D by 3. That is the required answer for this particular question. The distance from M at which the net force on M0, net gravitational force on M0 is 0, is R is equal to D by 3. And which is the option that agrees with this result? Yes, it is option C. A large number of identical point masses, each of mass m, are placed along the x-axis at 0, 1, 2, 4, 8, ... up until infinity. The magnitude of gravitational force on the mass at the origin will be, that is at x is equal to 0, will be, and the options are gm square, 4 by 3 gm square, 2 by 3 gm square, or 5 by 4 gm square. So let's see which one of them turns out to be the right one. And here is the system we are considering. We need the net force on the mass at the origin right here. I will name the other masses as 1, 2, 3, etc. And 1 is at a distance of 1 meter from the mass at the origin. 2 is at a distance of 2 meters. 4 is at a distance, or 3 is at a distance of 4 meter. 4 will be at a distance of 8 meter, and so on as mentioned in the problem. Now, there will be a gravitational force of attraction between each of these masses and the mass at the origin. So obviously, since all of these infinite or a large number of masses are attracting the mass at x is equal to 0, the net force on that mass must be to the right, and we will call it as F. And all individual forces are also to the right. So it becomes a one-dimensional problem. We don't have to use the vector notation here. We can handle right as positive, left as negative, and all the forces are to the right itself. So you don't have to worry about plus or minus also here. So if F is the net force acting on the mass at the origin, that will be equal to F1 attraction due to 1 plus F2 attraction due to 2, which will again be to the right, plus attraction due to 3, which is F3, plus F4, and so on until the large number of masses are taken into account. Theoretically, infinite. Agreed? So there will be infinite number of terms in this expression for the net force. Now let's substitute each one of them properly and carefully. The first force F is between these two, right? So it is G, M1, M2 both are equal to M, so you get M square by R square. The distance between them is 1 meter, so 1 square, plus F2 is the force between this and this. So it is G M squared by distance between them is 2, so 2 squared, plus F3 is the force between this and this. So it is G M1 M2, which is again M squared, divided by the distance is 4 squared. Correct? Let's write one more term. The fourth term will be G M squared, and the distance is 8. You remember, is 8 squared. So on until you reach infinity. Now you can see Gm square is common in all these expressions. So I'll have 1 plus 1 by 4 plus 1 by 4 squared, which is 16, plus 1 by 8 squared, which is 64, and so on up until infinity. So Gm squared into something inside the bracket. What is that something? That something is nothing but an infinite GP. It is an infinite GP with initial term 1. And what is the common ratio? First term is 1, second term is 1 by 4, third term is 1 by 16. That means term to term I'm going on multiplying an extra 1 by 4. So the common ratio is 1 by 4. So this is an infinite GP with initial term 1 and a common ratio 1 by 4. Now what is the sum to an infinite GP? We'll have to find out. So A is 1, R is 1 by 4. Remember that. So now let's go to the next slide. And this is the formula we require. Sum of the infinite terms of a GP will be A by 1 minus R, provided R is less than 1, which is the case here because A is what here? 1, and what is R? 1 by 4. So now let's find out the net force. What was it? F is equal to Gm squared into A. A is 1 minus 1 minus R, or 1 by 1 minus R. R was 1 by 4. So in the denominator I have 1 minus 1 by 4, which becomes 3 by 4. And when it reciprocates, it becomes 4 by 3. So the answer turns out to be 4Gm squared by 3. That is the required answer for this particular question. The net force is 4 by 3 Gm squared. And which is the option that matches with this result? Yes, it is option B. 3 identical masses M each are kept at the vertices of an equilateral triangle of side A. Find the force on A due to B and C. Options are root 3 Gm squared by A squared J cap, root 2 Gm squared by A squared minus J cap, root 3 Gm squared by A squared minus J cap, and option D, none of these. So obviously they ask us to take the horizontal as the x-axis and the vertical as the y-axis, and accordingly we have to select which option is the correct one here. So let us see that. So what is asked is the net force on A due to B and C. All the three have the same mass M. So there is gravitational force of attraction between any two of them. But since we want as to what is the net force on A. Now force on A due to B. Force on A due to B. So B obviously attracts A with the force F, let us say. And what is the value of that F? It is G. Mass of A into mass of B, both are M, so M square by distance between them is equal to what? The side of the equilateral triangle A, so A square. So F is Gm square by A square in that particular direction. Now what about the force from C? C also attracts A along the line joining them, correct? Along the line joining them with a force F prime, let us say for the time being, in magnitude. So what is F prime in magnitude? It is G. Again, the two masses are equal to M, and the distance between A and C is again A, the side of the equilateral triangle. So that will also be GM squared by A squared. So that will also be F. Now we need to calculate in which direction and what is the magnitude of the resultant force. So F resultant will be equal to root of A squared and B squared. Both the forces are equal to F. So F squared plus 2AB is again F squared. Cosine of the angle between the two forces, which is 60 degrees. Cos 60 is half. So it cancels off with 2 there. So I'll have root of F squared plus F squared plus F squared, which is root of 3F squared, which is root 3F. And F is GM squared by A squared. So it is root 3 GM squared by A squared in magnitude. What about the direction? Well, if we consider the resultant force by finishing the parallelogram and call this angle as alpha with one of the forces, because both the forces are of equal magnitude. So tan alpha formula is what? It is F sine 60 divided by the other force is also F plus F cos 60. F sine 60 is root 3F by 2 divided by F plus F cos 60. Cos 60 is half. So it will be F plus F by 2, which is 3F by 2. F by 2 gets cancelled. So I'll have a root 3 divided by 3, which turns out to be 1 by root 3. Tan alpha is 1 by root 3, which implies alpha is nothing but 30 degrees. So the resultant force makes 30 degrees with one of the vectors. It should also make 30 degrees with the other vector also. Why? Because the total angle is 60 degrees. So that means it has to be vertically downwards. So this force has to be vertically downwards. We had clearly defined horizontal along X and Y along the upper vertical. Now it's along the downward vertical. So as far as the vector or the unit vector is concerned, it is along the negative y-axis. So it is a minus j cap. So if you wish to write it in the vector form, it is root 3 gm squared by a squared minus j cap. That is the required answer for this particular question. The force is root 3 gm squared by a squared minus j cap. That is the net force acting on A, and which is the option that supports with this result? Yes, it is option C.